Hello class, it's time for section 2, which is called Ideal Stoichiometric Calculations. So we're going to get real good into the calculations of stoichiometry. Now remember, what is stoichiometry exactly? Well, like we talked about last time, it's the relationship between the reactants and the products, or the elements of the compound, and we are going to talk about the different calculations again. Briefly, we went over them before: the moles to moles, the grams to moles, the moles to grams, the grams to grams. So now we are going to do examples of each of them, and then in class you guys will do them by yourself. The objectives for this section: I would highly recommend that at the end of the video you rewind to the objectives and you see if you finally understand how to do each of them. So you will be able to calculate the moles of a reactant or a product from the amount of moles of a different reactant or a product. You'll be able to calculate the mass of a reactant or a product from the amount of moles of a different reactant or product. You'll be able to calculate the moles of a reactant or product from, can you guess what? The mass of a different reactant or product. And you'll be able to calculate the mass of a reactant or product from a different mass. So you will be able to go from moles to moles, from grams to moles, from moles to grams, and from grams to grams. So after this section, you guys, I have full faith that you will be able to do this. So once again, we talked about a conversion factor. Here, if we are given moles, we can use the mole to mole ratio to find the moles. This is in your book on page 288 if you need it. So then looking at mass to mass stoich problems. Once again, like before, if you are given the mass of a substance, you can use the molar mass, which is mass per moles, and that will give you the moles of a given substance. Then you can use the mole ratio, and that will give you the moles of the unknown substance. Then you can use the molar mass of the unknown substance and find the mass of the unknown substance. So now we are going to look at all the sample problems in your book. If you do not need me to go over them, we will be going over them and doing additional practice problems right now. If you do not need this, then shut it off. Look at the book yourself. But I would highly recommend doing these along with me. You will get better at this. Practice makes perfect. Even though no one is perfect, but we can do this together. Come on, guys. All right, looking at sample problem A, which is on page 289 in your book. In a spacecraft, the carbon dioxide exhaled by astronauts can be removed by its reaction with lithium hydroxide, which is LiOH, according to the following chemical equation. Okay, given the following equation, carbon dioxide, which is a gas, plus lithium hydroxide yields lithium carbonate plus water. So, how many moles of lithium hydroxide? So we are looking at lithium hydroxide, we're wondering this in moles, are required to react with 20 moles of carbon dioxide, the average amount exhaled by a person each day. So, once again, here's the equation. We can see that it is balanced. We are given an amount of 20 moles of carbon dioxide. and we want to know the amount of lithium hydroxide in moles. So how do we go about that? Using the mole-to-mole ratio. So we can see that 20 moles of carbon dioxide using the mole-to-mole ratio for every 1 mole of carbon dioxide, we have 2 moles of lithium hydroxide. So all we had to do was use the mole-to-mole ratio. We see that moles of carbon dioxide cancels out, and we get 40 moles of lithium hydroxide. 40 moles of lithium hydroxide. So, once again, we have 1 sig fig here. So we have 1 sig fig in our answer. And make sure we have moles of lithium hydroxide written. Very important. If it was just moles, we'd wonder moles of what? So moving on to another problem like this. So now we are doing a practice problem based off of sample problem A. So it says, the elements lithium and oxygen react explosively to form lithium oxide, which is Li2O. How many moles, so we're looking for moles of lithium oxide, will form if 2 moles of lithium react? So first things first, we need to write the equation. So we have lithium plus oxygen, is that right? No. Why? Because oxygen is diatomic, meaning that it will always have 2 atoms of oxygen together. So it's O2. Yield lithium oxide. Is this balanced? Also, no. It is very important for the equation to be balanced before we try to do stoichiometric calculations, because otherwise we won't get the correct amount of moles or grams or whatever we are looking for. So let's see how to balance this. First, oxygen, there's 2 over there. Let's put 2 here. All right, we have oxygen balanced, we have 2 on each side. Is lithium balanced? 2 times 2 gives us 4. So we need a 4 over here. So now, our known is 2 moles of lithium. So if we have 2 moles of lithium, we plug in the mole-to-mole ratio. So for every 4 moles of lithium, we get 2 moles of lithium oxide. And this will give us 2 times 2 is 4, divided by 4 is 1. So we get 1 mole of lithium oxide because the moles of lithium cancel out. And we see that our moles of lithium oxide has 1 sig fig because the moles given to us has 1 sig fig. So then we move on to looking at moles to mass. So if we are given an amount of substance in moles, we can use the mole-to-mole ratio of the given to the unknown and multiply it by the molar mass if we want grams. So if you are given the amount in grams, you would have to first use the molar mass before using the mole-to-mole ratio. But if you are given the amount in moles, you can go straight to the mole-to-mole ratio. So once you get the mole ratio, once you do that and get moles, if you only are asked for moles, you can stop here. But if you are asked for grams, you have to keep going and use the molar mass. So we will see that in sample problem B, which if you are following along in your book is on page 290. Sample problem C also goes along with this. That is on page 291. So sample problem B says, in photosynthesis, plants use energy from the sun to produce glucose, which is C6H12O6, and oxygen from the reaction of carbon dioxide and water. So we'll need to know this reaction. Luckily, I give it to you on the next slide. So what mass in grams of glucose are produced when 3 moles of water react with carbon dioxide? So let's look at that. So we are given 3 moles of water. Let's write that down, 3 moles of water. And we're looking for mass. So first, we need to figure out the moles of glucose. Using the equation, we can do that. We see that for every 6 moles of water, there's 1 mole of glucose. Again, this is a conversion factor, so we are not using the sig figs here. We will use the given sig figs. So if we stop here, this just gives us moles, so we need to keep going and use the molar mass of glucose. So the molar mass of glucose will give us grams of glucose over moles of glucose. So if this is not given to you, you guys know how to do this, but I will refresh your memory. So carbon, we know, has a molar mass of 12.01 grams per mole. Hydrogen, we know, has a molar mass of 1.008 grams per mole. Again, these numbers are coming straight from the periodic table. Oxygen has a molar mass of 16 grams. So, since we have 6 carbon, 12 hydrogen, and 6 oxygen, we need to multiply these. 6, 12, 6. This is the number of moles there are. And then we would add that up, giving us 180.18. 180.18 grams per mole for glucose. 180.18 grams per mole. We see moles of glucose cancel out, moles of water cancel out. So we would say 3 times 180, or we can even say 3 divided by 6 would give us 2 down here. So 180.18 divided by 2 would then give us 90.1 grams of what? Glucose, C6H12O6. This gives us our answer in grams, which is the mass. Okay, so if we look at a practice problem that's similar to sample B, which we just did, it says sulfur dioxide, which you guys by now know is SO2, is an unwelcome result of burning soft coal in power plants. So it is an air pollutant. Some of the SO2, sulfur dioxide, ends up as sulfuric acid in acid rain. The net reaction is as follows. We have sulfur dioxide plus oxygen plus water yields sulfuric acid. So we want what mass in grams. So we want mass in grams of SO2. So we are looking for grams of SO2 is needed to react with 37.5 moles of O2. So let's look at it. We have, I'll start over here, 37 0.50 moles of oxygen. Because it starts in moles, we can use the mole-to-mole ratio. So we see that for every 1 mole of oxygen, we have how many moles of sulfur dioxide? 2 moles of sulfur dioxide. If we were just looking for the moles, we would stop here, but we are not. We are looking for the what? The mass in grams. So we keep going, and we want to end up with grams here. So we need to use the molar mass now. So how do we figure that out? We know that there's 1 mole of sulfur here and 2 moles of oxygen. Therefore, the periodic table tells us that sulfur is 32.06 grams per mole. And oxygen has a molar mass of 16 grams per mole. But since there's 2 oxygen, we multiply this by 2, giving us 32. 32 plus 32.06 gives us 64.06 grams per mole of sulfur dioxide. So we see the moles of sulfur dioxide cancel out, the moles of oxygen cancels out, and if we type this into the calculator, 37.5 times 2 times 64.06 gives us 4,804.5. But 4.5 grams, but because our given is 1, 2, 3, 4 sig figs, we would round this to 4,805 grams of sulfur dioxide. So moving on, if we are given the mass and we need the moles, we can use then the molar mass of the given to get moles, and then we can use the mole ratio, and then that will give us moles of the unknown. So if we look at sample problem D, we skipped C because it is very similar to B, and then we did a practice for B. So looking at sample problem D, the first step in the industrial manufacture of nitric acid is the catalytic oxidation of ammonia. So here we have ammonia, oxidation, so oxygen is added, and this yields nitrogen oxide and water. So the reaction is run using 824 grams of ammonia and excess oxygen. How many moles of NO are formed? So we are starting with grams and we want to get moles. And how many moles of water are formed? So if we look at the solution, we can see that we are given mass of ammonia. We want the amount of NO and we want the amount of H2O in moles. So we wrote out the equation again, and so we start with 824 grams of ammonia. What do we need first? So we need the molar mass of ammonia. We know that nitrogen is 14 and hydrogen is 1, giving us about 17.04 grams per mole. So this is of ammonia. We are using the molar mass. But we want to know the moles now of NO produced. So we look at the formula, the equation. And for every 4 moles of ammonia, we see that 4 moles of nitrogen oxide are produced, giving us a grand total of 48.4 moles of NO. We see that the moles of ammonia cancel out, the grams of ammonia cancel out. Great. Now what about for water? Here we can just go and erase this and this, and we're still using the same equation. So we see that for 4 moles of ammonia, there are 6 moles of water produced. And then that, if we calculate that out, that gives us 72.5 moles of water. It says, chlorine gas can be produced commercially by passing an electric current through a concentrated solution of sodium chloride, which is also known as brine, salt water, sodium chloride, brine. This equation is as follows. NaCl plus water yields sodium hydroxide, chlorine gas, and hydrogen gas. So, if the brine contains 250 grams of sodium chloride, how many moles of chlorine can be produced? Let's look at this. We have 250 grams of sodium chloride. We want to know moles of chlorine, so we must first find the molar mass of sodium chloride. Sodium is 23 approximately, and chlorine is 35.45. So, adding that together, 35.45 plus about 23 is 58.45 grams per mole of sodium chloride down here as well. So then we look at the equation. For every 2 moles of sodium chloride, we get 1 mole of chlorine. For every 2 moles of sodium chloride, we get 1 mole of chlorine. So if we do the math out, we say 250 divided by 58.5 times 2, so divided by both of these together, gives us 2.14 moles of chlorine. But because we only have 2 sig figs in our given quantity, we would then just have 2 in our answer. But how many moles of hydrogen can be produced? We can see that the ratio is the same from sodium chloride to chlorine as it is from sodium chloride to hydrogen. This can now be an H, giving us the exact same amount of moles. So if we were then asked, I should delete this. If we were then asked to go from mass to mass, we would go one step further and use the molar mass of the unknown quantity that we want. So we would have the given mass, use the molar mass of the given substance, then do the mole ratio, and then use the molar mass of the unknown substance. So once again, this is just another picture to show you how to get there. If you want to screenshot this, or if you want to take notes off this, you can pause the video here. So we are going to look at sample problem E. Tin 2 fluoride, which is SNF2, is used in some toothpaste. It is made by the reaction of tin with hydrogen fluoride according to the following equation. How many grams of tin 2 fluoride are produced from the reaction of 30.00 grams of hydrogen fluoride with tin? So this, if you want to follow along, is on page 294 to 295 in your book. So we are going to look at 30.00 grams of hydrogen fluoride. We need to know the molar mass of hydrogen fluoride first. And then we go to moles of hydrogen fluoride. So, using the periodic table once again, we can figure out that the molar mass of hydrogen fluoride is 20.01. 20.01 grams per 1 mole. And then we look at the equation. We see that for every 2 moles of hydrogen fluoride, there is 1 mole of tin 2 fluoride. But now, we're not done yet because we don't just want moles. We want grams. So we need to know the molar mass of tin 2 fluoride, which is 156.71 grams per mole of tin 2 fluoride. Tin 2 fluoride. And we see that we put the mass on top here. It's on the bottom here because we need to divide by the grams to cancel them out here. And here we are dividing by the moles of hydrogen fluoride to cancel that out. And then we use the molar mass of tin 2 fluoride to cancel that out and get our answer in grams, which is 117.5 grams. 117.5 grams of tin 2 fluoride. Do we see why we have 4 sig figs? Once again, we're starting with 4, we are ending with 4. These are just conversion factors that don't count towards the sig figs. Now we are going to look at a practice problem that goes along with sample problem E. So sodium peroxide, which is Na2O2, reacts vigorously with water in the following unbalanced equation. It says that it's unbalanced, so what do we need to do first? So first, we must balance the equation. We notice, let's start with the sodium. There are 2 on this side, we need 2 on this side. That then gives us 4 oxygen on this side, but we only have 3 on this side, so let's put a 2 here. Now, our hydrogen is off balance because we have 4 hydrogen on this side, so we need 4 on this side. So let's get rid of that and put a 4 here, giving us now 4 sodium. So let's put a 2 over here. 2 times 2 is 4. Our sodium is set. We have 6 oxygen now, but we have 6 oxygen on this side, and we already set our hydrogen. So now the equation is balanced. So what mass of oxygen is produced when 50 grams of sodium peroxide react with water? So we are looking for the mass of oxygen. So this in grams. When 50 grams of this react. So let's look, 50.0 grams of sodium peroxide. So we need the molar mass of sodium peroxide, which is 77.98 grams per mole. We can cancel out the grams now. And then we can use the equation for the mole ratio. So for every 2 moles of sodium peroxide, we get 1 mole of oxygen. But are we done yet? No, because we want the mass, and mass is not in moles. Mass is in grams. So we know that the molar mass of oxygen, because it's diatomic, we have to multiply what's on the periodic table by 2, giving us 32 grams of oxygen per mole. And then when we calculate this out, we get 50 times 32 divided by 77.9 times 2, giving us 10.26 grams of oxygen. Ooh. So that gives us the mass. But sig figs, are they correct? No. Let's go up here. Because we start with 3. 1, 2, 3. Our answer must have 3 grams of O2. 10.03 grams, 10.3 grams of oxygen. So now looking at this, what mass in grams of water is needed to completely react with the sodium peroxide? So let's erase this. We can keep this so far. We have the grams. All we need to change is the mole-to-mole ratio, because for every 2 moles of sodium peroxide, we get 2 moles of water. 2 moles of water. So this pretty much cancels out, this whole thing, the 2 to 2, and the moles cancel here, and then the moles will cancel down here. What is the molar mass of water? 18.02. Then when we do the math for that, we get 11.6 grams of water. 11.6. All right, thank you guys for listening, and stay tuned for section 3 where we'll talk about limiting reactants.